Hi students, you requested a little bit of help with this lab, experiment 15. So here we go. So you're working this lab, and the first thing it asks you is the brand name of the aspirin. Now, sometimes that will be on the bottle and sometimes it won't be on the bottle. So if you see a bottle of Bayer aspirin there, go ahead and write, oops, I guess I got to turn the pencil on, don't I? Okay, there we go. Go ahead and write Bayer there. Or if there's Kroger or whatever, go ahead and put that. If you don't see the brand name of the aspirin, don't worry about it. Just put a line there. Now, the next thing you guys will see is molarity of NaOH. So NaOH is the base that we're going to put in the burette. So that's that long cylindrical glass thing that has all the graduations on it. Now, the molarity. So what we'll do is we'll read the bottle and we'll go ahead and go, okay, it tells me that the molarity of the NaOH is 0.0900 molar. And remember that the big M right there means moles per liter, just to remind you. Okay, now you're going to do a couple of trials with this. And what we're going to do is we're going to fill this long thing with base. So what you'll have up at the top here is a funnel, and it'll go down into the burette. And then on the bottom here, what you'll have is this, and you'll have an Erlenmeyer flask down here. Okay, and then you'll put the base, which is this stuff right here, into here, and you'll fill it up, and then you'll take the funnel out of there. So let's pretend that the funnel's not there anymore, and we're going to see that we have a meniscus there, and the meniscus does not need to be on 0. So say up here we have 0, and the burette is most likely going to read in milliliters. And say right here we have 1 and then 2 and 3, etc. So we're full up with the base here, and we're going to drip it down into the aspirin solution that is down there. Okay, so we want to put what our initial burette reading is. And let's say the meniscus hits like right on 1. So what I would do is I would read the burette and I'd go, okay, I've got 1 milliliter, but I know that I have to go ahead and make a guess there. So maybe I think it's exactly on 1.0 and it's not 1.1, but my partner thinks it's 1.1, and that's okay because this is our unsure digit right there. Now, if you have a burette that has little lines in between 1 and 2 and between 2 and 3, etc., then you would have another digit right there. So make sure you're reading your burette and writing down the correct number of significant digits. So remember, you always have to make a guess. Now you can write milliliters right here, but it's already right there, so we can move on. All right, so now you're gonna open up this little thing right here called the stopcock, and when it is perpendicular to the burette, it's closed, and when you rotate it so that it is parallel with the burette, it's open, and the base will drip down in there and react with the acid. So what we're going to see is, oops, that was a terrible line there. So imagine that that's straight right there. Oh, that's awful. Let's see, let's redraw that. Okay, let's make it straight. There we go. Okay, so we're going to drain down the base into the acid down here until we get the lightest shade of pink we've ever seen, and then we know we're at the end of our titration. And and say we end up down here at 42, okay? So the burette, we read it backwards from the glassware that we usually read. So with a graduated cylinder, the thing that looks like this, what we have is we'd have 10 at the top and we'd have 0 at the bottom. So we're used to reading the big number on the top and the small number on the bottom, but the burette works backwards. You'll see the small number on the top and the big number on the bottom. Okay, so since all we see is to the ones column, which is right here on the burette that I just drew, and remember, I'm just making this up. The burette you're looking at might go to the tenths column, which would be right here, which would mean you would have to make a guess to the next column over, which would be the hundreds. Anyways, I'm going to read it at 42, and then I don't have graduations in the tenths, but I need to make a guess over there. So again, I'm just going to guess that it's exactly at the 0 mark right there. And my partner could look at it and say, no, that's 42.1. And that would be okay because remember that last digit is our guess. That's where we have wiggle room. Okay, so again, this is milliliters, and you can write that there, or you cannot because it's already over here. But if it wasn't over here, you would have to make sure that you write it in. It's always good practice to go ahead and just write it again. All right, so now it says volume of NaOH used. That means how much volume dripped down into here. So how much did we drain into the Erlenmeyer flask? And what we do is we do 42 minus 1, and that's going to give us what? 41. And if we're using the significant digit rules for addition and subtraction, we have that this number goes to the tenths, this number goes to the tenths, and so our answer is going to go to the tenths. Now we're going to convert 41.0 milliliters to liters. So we're going to have to divide 41 by 1,000 because that's how that works. And you guys would have learned to do that way back in week 1 of this class in chapter 1. So if you divide that by 1,000, what we'll get is 0.0410, keeping the 3 significant digits there. And again, liters is already here, so you don't have to write it, but it's good form to go ahead and write it again. Okay, not bad so far, right? And then it says, magically transform this into grams of aspirin in 2 tablets. Now, you can't just weigh the 2 tablets of aspirin on the balance because aspirin tablets not only have the aspirin molecule, acetylsalicylic acid, but they also have a starch in there and a coating around the pill so it goes down easy, and all of that stuff adds weight. So what we have to do is we have to do some stoichiometry here. And what we're going to want to do is we're going to want to go back to this page right here. And we're going to see that our acetylsalicylic acid, so that's this word right here, and that's the other name for aspirin, is this molecule right here. And even though that's a giganzo molecule, it works the same way as the little acid HCl right there. So it will react with a base, and it will give us a salt and water. And you can see that we've got the salt right here because we've got the positive ion, the cation, and we have the negative ion, which is the acetylsalicylic acid molecule without the hydrogen right there. So you can see right there that the hydrogen has been given away, which is what acids do. They give away H+, and you can, oops, sorry about that. Bad teacher bat. Okay, you can barely see the O- right there. So there's a negative sign. So remember with NaCl, The other way that we could write it was Na plus and Cl minus. It's just that when we put them together in a formula, you don't have the charges. But in organic chemistry, which is the chemistry that you would take after you take a year of general chemistry, which is after this class. Once you get there, we do kind of funky things. Like organic chemists like to write the anion first because it's kind of the molecule or the ion of interest. So you can see that this guy right here, that is the anion, is written first, and then we write the cation second, which is the Na plus, and we leave the charges there, which we never do in this class, but organic chemists are funny people, and they're like, we like to do it this way. But don't worry about that. It's doing exactly the same thing as this simple acid-base reaction right here. And what we can see in both of these equations or both of these reactions is you have one acid reacting with one base to make one salt and one water. So you have one acid here. So we'll nickname acetylsalicylic acid as ASA. So you have one ASA and you have one base and you have one salt and you have one water. It works the same way. So you need one of each for this reaction. And that's going to help us when we need a multimole ratio in the calculation that we're going to do right now. Okay, so how you figure out the grams of acetylsalicylic acid is this. Okay, so I'm going to use a space down here. And we're going to take this volume right here. Now remember, I just made up the concentration of the base and I made up how much of it I used so I could show you guys how to work this. Don't write my answers for your answers because you will have different answers. I'm just showing you the process how to do it. Okay, so we've got 0.0410 liters of NaOH. Okay, now somehow we want to get from liters of NaOH to grams of aspirin. Well, just take a first step and say to yourself, I need to get rid of liters. So do I have anything that will allow me to get rid of liters? And remembering that once you get into moles, you can do a multimole ratio, so you can go from one substance to another substance. So we'll go ahead and set up a conversion factor, and then we'll go back up here and we'll go, oh yeah, I had moles per liter there. Remember the big M means moles per liter, and this is NaOH. So I have 0.0900 moles of NaOH per liter of that solution. So for every 1 liter, I have 0.0900 moles of NaOH. Yay, I got rid of liters. Okay, now I'm in moles. And whenever I'm in moles, I can do a multimole ratio and I can go from one substance to another substance. So let's go ahead and put moles of NaOH down here because that's what we want to get rid of. And where do we want to go? To which substance? Aspirin, okay? So let's go ahead and put moles and we'll abbreviate it as ASA for acetylsalicylic acid, which remember is aspirin, okay? Now where do I get the numbers that I put into the multimole ratio? As always, I pick them right off the balanced equation. And look what we did back here. We have a 1-to-1 ratio. So we go ahead and we go, okay, for every 1 mole of NaOH, I'm going to react 1 mole of ASA, okay? Now I'm in moles of acetylsalicylic acid, and you guys know how to go moles to grams and grams to moles, so let's go ahead and do that. And whenever we have moles to grams or grams to moles, that conversion factor is called what? A molar mass. So for every 1 mole of acetylsalicylic acid, we want to know how many grams of acetylsalicylic acid do I have? And I'm trying to squish it in the end there. Okay, so you could look this up, or you could take a look at this molecule and go, oh my goodness, I have this many hydrogens and this many carbons and this many oxygens. Or you could take a look in the lab. I know it is somewhere. Yes, it is right there. The acetylsalicylic acid has a molar mass, also called a molecular weight, of 180 grams per mole. If you look this up on Google, you'd probably find that you could get another significant digit, so 180.2. And where did I get that? I asked my friend Wikipedia, okay? And I know your other professors are like, oh my goodness, don't use Wikipedia. But for most chemistry stuff, I found that it's pretty right on. So I'm pretty comfortable using that. Okay, oh, by the way, we got to cancel out moles of NaOH and moles of ASA, and we're left with grams of aspirin. Oh my goodness, that's what we were looking for right there, right? Woohoo! Okay, whiz bam bang, you do this on your calculator, and what you're going to get is 0.664 grams of acetylsalicylic acid. Now again, that most likely won't be your answer. That's my answer because I made up the volumes and the concentration of NaOH, but this is the exact same process. You just got to plug and chug. Now this is looking pretty good because aspirin tablets tend to be 325 milligrams a piece. And 325 milligrams is the same as 0.325 grams. And we have 2 tablets. So if we multiply that by 2, we would get 0.650 grams of acetylsalicylic acid. And what I have here is 0.664. So that's pretty close. We're pretty good there, okay? So I would go ahead and I'd put 0.664 grams. And then you guys would do another trial and you'd have another value there. And then you'd go, okay, percent of labeled amount of aspirin, what on earth is that? And you'd go back to this little equation here and you'd read it and you go, there seems to be something wrong with this. Okay, first of all, on the bottom, what they've got there is they've got grams, but they've got milligrams on the top. So that doesn't quite work. And also this is 0.648 instead of 0.650. And I have no idea why it's like that. And everybody who wrote this lab manual is long retired, so I can't ask them what on earth the difference is there, but we're going to go with 0.650 because the bottle says each tablet should have 325 milligrams, which is 0.325 grams of acetylsalicylic acid in the pill, okay? So what we do is we use Professor Gray's new equation, which is whatever you got on top divided by 650 grams on the bottom times 100. And I'll go ahead and write that down here. So what I would do to get percent of labeled amount is I say, okay, I'm going to have 0.664 grams of ASA, which is my experimental value, divided by my theoretical value, which is 0.650 grams of ASA, and then grams of ASA cancel out, and you multiply that by 100. You put that into your calculator and you get 102%. So I got a little bit more than 100%. And usually when you get more than 100%, that means that you still have a little bit of water in your solid, so it needs to dry a little bit more. In general, that's what that is. So for this one, you would put 102%, and then you do the math for the other one, and you'd get some value there. And then it says the average. So what you would do is you'd take this value and you'd add it to this value, and you'd divide by 2, and you'd end up with this value. And it says, does your aspirin meet the assay requirements of the USP? Okay, so what the USP says is that you can only be 5% off, and that's plus or minus 5%. So 0% off would mean that you had an average of 100% right here. So 5% off means that your average percent can be from 95% to 105%, because that's 100% plus or minus 5%. So if you're in that range right there, then you would put yes. So if I got 102 and then I got something very similar for this one and averaged out to somewhere between 95% and, oops, wait. Yes doesn't go there. Yes goes here if you have 95% to 105%. Okay, so that's how this lab works. I hope that was helpful for you guys, and I will see you next time. Bye-bye.